And there's a few things here in this. And I kind of hem and haw and sort of move back and forth personally in terms of how I think about these statements. Lies, damn lies, and statistics, which is a very common idea, but I've always thought I'm just not as dogmatic about this. And that is, it's not the statistics that lie, it's the ignorant that read. Now, I used to be very dogmatic about that really you cannot lie with statistics. And I think in the most rigid way possible, that is really true. Like if you truly understand every aspect of the stats, you can't pull someone over, and can't sort of pull the wool over their eyes with statistics. They will see the fallacy in what you're doing, or the fact that you don't understand what you're doing, you're just presenting something. I'm not sure that's a fair statement in the sense of, I'm not sure that level of expertise really should be required to deal with it. But I will make this statement, and that is the vast majority of the issues, the vast majority of the incongruence we have when we're trying to understand statistics is not about the stat, it's about the audience. It's about not understanding. In this class, and I've said this before, and I continue trying to say this, I'm not here to have you memorize a suite of things. There are a few things you have to memorize. What I'm here to do is to try to help you to learn how to think through these things, make choices about these things. When you read something, see what it is telling you. That's my goal for you. And not that I expect you to be complete by the end of the semester. What I expect you to be is more adept at developing your own abilities and continuing in this process as you grow in this. I am very thrilled, and this happens every single semester, as I have students coming back doing two things. One, they will argue over points that I taught very hard. I like this thing. They come back, yeah, Gunnels, I don't think so anymore, man. And they're bringing me sort of data, and they're bringing me sort of papers that are giving me good arguments about my declarations. I think that's awesome. That's how we sort of operate. That's good science. The other thing is people sort of come back and they're doing new things and new ideas with things that they got here. That's what you should be doing. So let's take this statement as an example. The statement was stupid. The statement came from the CDC, and the statement was stupid. We just went through a global pandemic. We're not in the epidemic phase. It's still very prevalent, but it's going to be sort of kind of a recurring thing with COVID-19. And the statement is really problematic. For 6% of the deaths, COVID was the only cause mentioned. What makes that statement so problematic? And one of the things about statistics is you have to understand not only the numbers, you actually also have to understand the system. And in this case, the system would be healthcare. As you are biologists, what makes this statement so misleading? 6-month period. 6-month period. But with the percentage change based on the amount of time. So the percentage probably should be equivalent. It might go up a little bit, up and down, up and down, up and down, but that's standardized for the time frame. Joy, did I see you? Did I see you with a hand? Did I see you? Messing? And I'll come back. Okay. Diana? Only, that's an interesting choice of words. No, 100%. And I'm going to use this as sort of the example. Now, you guys are the children of COVID. I am square one, the child of HIV. You know, I was going through puberty as it was identified as gay man disease. I was sort of in my middle teens, late teens, as we first identified what the virus was. I was in college as really the scare went through, and LGBTQ communities were being harassed and sort of demonized because of it. And one of the things with HIV that was one of the points that made it dismissible was the fact that HIV kills nothing, kills no one, never has. No one dies of HIV. No one dies of the virus, even though just a few years ago, 700,000 people died from complications associated with HIV. No, you don't die of HIV. HIV destroys your immune system. You die of complications of other things that then actually kill you. Your T cells, other things are there. So one of the things that came out early was dismissing it because no one's dying of HIV. They have these other issues. And it sort of distracted effort, distracted time, because it's a correct stat in some ways, but it really misleads the point without understanding of the statistics, and in this case, also understanding of the biology. Make sense? So this one, I want to give you guys 3 minutes on. What is the association between statistical lies and being misled by statistical ignorance? Now, what ITS makes no sense, because this monitor was working and it was mirroring just fine. He got lucky. Good for him. Virtual land, you guys should talk to each other. Dominic, if I don't get you up, just give me a yell.
Oh, wait. You don't have to like understand and words in such a way that it was influenced something else. Right. We don't understand that. We don't. Like, yeah, we're not educated in that field, like words in words in such a way that really got my and you won't be able to say like, wait, you don't know.
Okay, Gil. Well, maybe, sure. We can explore differences, we can explore similarities, and maybe that'll give us both points of association. Oh, I think it's actually very fair.
Get the wrong idea. It's a lie or
It both leads to a misunderstanding. Like, not a statement, but I gave you the quote from CDC. Do you think the CDC is trying to underplay COVID? And I said, no. Are they trying to sort of minimize the concern they had, especially you guys remember 2020, September, in that period of time. The CDC sort of saying, oh, this is wrong, no big deal. Fire plagues, you'll love it. No. But so as a same result, so I like that. One, it can just provide misinformation. Jonathan, give me another. Yeah, I would almost say, yeah, you can certainly and absolutely lie. I think that's why I got away from the dogma. But I'm also very much of the opinion, and this may be inaccurate, and there's evidence to demonstrate that, most scientists, and by most I mean 99.999%, do their work above board. They're doing it ethically, they're doing it intentionally, they're doing it honestly. They will make mistakes, and every once in a while you do have bad characters. So there can be individuals that literally lie and then can use that to mislead. And that may actually occur more often than I care to admit. Did you all see that study that came out of Denmark, I think about a year ago? Where a third of postdocs, graduate students, and assistant professors said that they had published data that was not totally above board. There are two things you should notice. What population did I say did this? Graduate students, postdocs, and assistant professors. A third of them said they had done this at least once in this anonymous survey run through Denmark's Scientific Society. Anyone missing from that group? The full professors, the associate professors. Maybe they're just good people, or maybe they couldn't admit it. I can't say, but I was shocked by those data. This is an anonymous survey, came out of Denmark, surveying researchers there, and a third of the junior researchers had acknowledged at least once doing something inappropriate with their data. So that would go in line with Jonathan's statement. Yeah, there can be some lying, and of course that can mislead. Gabrielle, would you go to offer? Okay. What's the association ultimately between these things? Fabiola. Yeah, lies and ignorance.
More ignorant about the topic or the things that's being stated in order to get your point across.
Do you all know how Americans accept evidence? How Americans come to believe what they believe? Statistics, oh, you're so lovely. No, not statistics. Warm, it's not about importance. Definitely not majority, not our community, not our society. It's who they trust. They trust the assertion, they trust the information that comes from the individual they value as being a good source. This is one of the reasons why in our country, we have a difficult time when you present evidence that contradicts let's say, a popular assertion. Because if you hear the popular assertion from someone you trust, you take that perspective, you absorb that perspective. And then you sort of lock in and become more entrenched to that perspective. Well, if you trust me, and whether I do this willfully or accidentally, I give you misinformation or information that is unclear. If you trust me, are you likely to accept it? And the answer is yeah. And do you have anything to really govern yourself in terms of that acceptance? And I think that's where statistics are more unique than other forms of communication. You know, written communication, we all are pretty good at reading and reading logical fallacies and reading sort of logical arguments that just don't make any sense, or reading the fact that someone's making a statement, there's no evidence that sort of underlies that, and we can kind of quickly dismiss it. You know, sometimes we get in the trap, and we've all done this, and I definitely have done this, where you read something and maybe it just clicks with you and like, oh, that's so exciting. And you just kind of want to take it, and you just want to go with it. I had someone yesterday sincerely talk to me with great enthusiasm about the Yeti footprint at a Disney ride, as this was the Yeti footprint. It is a person who is brilliant, but this was true. This person also is a fanatic about Disney, and therefore they've decided that this is their trusted source. They didn't say that, but this is therefore true. There is a Yeti in the Himalayas, they have the footprint, and it is Disney. It's awesome. But I think the issue with statistics and why it's so prone to confusion is because of the level of ignorance that we have to deal with. You, and your job, is to become better. Okay, so I put this up there because this is really about p-values, and this is really, I think, a very, very true statement. We started to get this a little bit on Tuesday. Imperfect use and or understanding of confidence intervals is much less problem than incorrectly using and or understanding p-values. There's a simple reason why. Imperfect use and misunderstood p-values is a threshold of A or B. If you don't know what you're doing with it, and you treat it as absolutes without understanding why the threshold is the way it is, and you treat it as a strict thing where a p-value of 0.51, just 0.1% above 5%, is fundamentally different than a p-value of 0.49, 10% below threshold of 5%, as if that sum threshold gives you a difference of whether you describe random patterns or non-random patterns. That's very dangerous. There's no gray, no subtlety. It's an absolutism. And that can lead to a lot of problems just simply because of how simplistically it's being used. Where confidence intervals, and we talked about them, describe the degree to which your measured mean matches where a true mean is. Your sample mean matches the population mean. You can get confused about 90% versus 99%. Like, man, you can look at a figure that's 99% confidence intervals like, wow, that's a lot of error. This is going to be a huge error bar, right? 99%. To be confident 99%, you have to have a wider range. You could miss that. You can be just confused on that. That's okay. You still got a concept for where that true population mean is. And you compare that true population mean to some other true population mean. And even with that visualization, you get some sense of whether they're overlapping or not, and whether they are randomly different or whether there's maybe a biological difference that requires you to think through it in ways that poorly understood p-values do not. If you would do me a favor by the end of the semester, when you look at your p-value, which will always be the first thing we do, it is an incredibly valuable tool. But by the end of the semester, you look at it, you recognize it's the first step. You then move on to the next and more interesting things. 2, you look at it and you recognize the number is telling you something and you have to make a decision. Not the number tells you what to do. The number informs how you then decide. If you get to those 2 steps by the end of the semester, I've won. Yay, life is good. Cool? And then last, this is really important. We use a ton of things after the p-value. In statistics, we start with a p-value. It allows us to say whether we're going to be talking about random, we're going to be talking about non-random distributions, random or non-random pattern. But then as soon as we do that, we're looking at figures, we're looking at descriptive statistics, we're looking at confidence intervals. That's the meat of the information we're going to be excited about. When we talk about random patterns, it's pretty easy. There's not a lot to do after that. You're just talking about the fact that things are similar. Things are not correlated. When there are non-random patterns, then you get into the juice of it. And the juice of it, again, is really a thought process. It's not an absolute process. Correlation coefficients, not absolute. P-values, ultimately, not absolute. These are all just tools that help us understand the science. Cool? Questions with that? I'd take 5 minutes, make a transition, come on back. When we do, we are on material that will not be part of the exam. So if there's a last question before the exam, you can ask it at that point, and then we're done with any questions about the exam. All right? Okay, 5 minutes, come on back at my clock, 4:16. Virtual land, go take a break for 5 minutes. All right. Let's get back. This unit's pretty small. It's sort of, and it's also sort of our last, let's say, statistical philosophy unit. After this, it's all sort of tests, experiments, observational studies, work. But it really addresses sort of 3 really dumb and annoying things in stats that we give way too much attention to. And therefore, they are the 3 evils: normality, outliers, and transformation. Mitalski is more traditional in how he thinks through these 3 things: normality, outliers, and transformations. But even he is, I'm not gonna say impatient, but he's not terribly bothered by it. These 3 things tell me a lot about a researcher. When someone gets really cagey about outliers, they're one of 2 people from my perspective. And that is, they are a statistician who knows nothing about the data they're looking at. They're just keen on numbers. And they love the numbers. And it doesn't matter whether it's something about a cell or something about a demographic population of people living in Fort Myers or about rats on an island off the coast of Alabama. They don't care. They're just numbers. And they love them. And for that group, outliers are great. Or they really don't understand statistics. They know how to click a button to do something, but they don't understand what they're doing. So that's one group. Normality used to really be a problematic thing because you can either do a good procedure, what are called parametric procedures that require normality, require homoscedasticity. These are valuable things that you had to have in order to use traditional things like a regression, a t-test, an ANOVA. These are good. And if you didn't have those things, then you would have to do something called a non-parametric test, which is totally goofy. And we'll talk about it later because you guys will do non-parametric tests and you all are going to simulate a non-parametric test. And that will probably be the most annoying day in class. So it's coming. But it's really not that big of a thing anymore because we really don't have to bother with it. There is Bayesian, 1, and 2, there are what are called permutative tests that allow you to avoid issues of normality in terms of the analyses. So we're going to go through sort of traditional and give you some insight there, but then we'll talk throughout the semester about 3 different approaches: parametric, which requires normality, homoscedasticity; non-parametric, which is sort of a traditional way to avoid those issues; and then permutation, which is a more robust way to actually deal with traditional inferential statistics with biological data. And then the last thing we'll talk about is an offshoot of outliers, and these are things called transformations. And I always thought transformations were weird. I mean, just straight up bizarre. But again, as I said, I was not a very good student. If I thought something was stupid, like just logically was dumb, I didn't think the professor was dumb. I was just like, this is stupid. I had a very difficult time getting past that. Genetics struck me as stupid. We had not really got into the science of gene expression yet. We were still in genotype equals protein equals phenotype. That's dumb. I mean, you didn't need to be that smart to realize, oh, hell no. There's got to be more going on than sort of 2 alleles for 1 loci, creating multiple different phenotypes. No, we weren't these carbon copy type of Sesame Street representations. There was a lot more variation. Obviously, with gene expression, that became fully obvious. Transformations struck me as sort of that old perspective. Just, it was so weird. But we're going to learn about it. We're going to do it because you're going to have professors like you need to do a transformation. And if you are their student and they tell you you need to do a transformation, what is your job? Absolutely, you do a transformation. You're like, this is great. I love transformations. Can we do a square root transformation? How about square root plus 1? Because we got some zeros in our population. We know how to deal with that, right? You do it. So again, this is biostats according to Gunnels. You work with your population, and then you also maybe make your choices and make your arguments. So first things first, I want you, maybe on a computer and paint, maybe on a pen and paper, I want you to draw your favorite distribution. Maybe you have multiple favorites. Doesn't have to be one. If you want to, you can look up online, look at data distributions and see what looks good to you. I want to see your favorite distribution. Virtual land, same with you guys. In fact, in virtual land, I can have you guys show your distribution more easily than anybody. Oh, and today's going to be a light R day. Light R. Love it. Favorite distributions. Emmanuel, buddy, go and share your screen. Let's just see your favorite distribution, if you can do it. Closed captioning is actually pretty good. That's not bad. Let's go. Well, that's actually true too. Coffee's pretty good. Misty, what's your favorite distribution? Yeah, here. Ooh, that's Poisson distribution. Love that. Love that. Ashley, what's your favorite distribution? Let's see it. Poisson distribution is famous in ecological models because it is the null distribution for organisms that are randomly distributed across the two-dimensional landscape. That's how I expect them to be. Where the x-axis would be the number of individuals within a group. And what did Ashley give us? She got a nice bell curve. Absolutely. It's a favorite of many people. Loving a bell curve. Madison, nice distribution. Well, that's the last one. Let's get one more. Ooh. Oh. When do we see that distribution? That's one of my personal favorites. When do we see that distribution? Multiple modes, and what example of selection in terms of natural selection tends to create this type of distribution? What's that? Not heterozygosity. No, I like that. I like that. Not heterozygosity. Stabilizing, directional, or disruptive selection? Disruptive selection. And what's a classic animal that shows us this type of distribution? Finches, not so much finches. I like finches. Finches are cool. Not moths. In fact, most people don't like these. I like them. Most people don't. Theo Wilson like them. Sometimes wasps, but they're not the famous ones. Not the big ones. I like wasps, but yeah, not ants. Ants. Where you have like a minor worker, a worker, and a soldier, and you get to sort of these trimodal distributions, sometimes quintimodal distributions, which are just cool. As you get negative selection against anything in between. So as I was walking around, I don't actually remember who said it, and you can volunteer. It's a fair comment. Someone's like, yeah, distributions are boring. And I was thinking, okay, sure. But I remember being in graduate school where I went with a bunch of students who were theoretical biologists, and we took a class, and they went out and they bought the biology of data distributions. And all it was a book with those. And then a mathematical model underneath it for how you produce it with different sort of functions. It's awesome. Awesome. And they do. That's one of the things about biology. Biology ascribes to many different types of distributions. You know, I said this is ecological, but this is also disease. Disease, if it's randomly distributed within a population, should show this type of clustering, where you get a few areas where a lot of people are infected. You get a lot of different areas where very few people are infected, and then it sort of tapers off. Same type of thing, if it's randomly distributed. And therefore, you can actually test against randomized processes by comparing to Poisson. Normal, very important distribution, not even just so we don't see it, but a lot of times we want to test against whether that is what is going on. In fact, today, when we do a test, we're going to be testing against normality. And then I do have a fuzzy camera for those. Because I do like my social insects a lot. So some other very common ones, and actually a really important one that frequently gets overlooked, and that's a uniform distribution. where all things are equal, likely across the data. And this one does occur a little bit in biology, but it's incredibly important in terms of modeling and in terms of setting seeds in order to construct simulation models. So very valuable. Bimodal, trimodal, very important. Frequently shows up as null, sometimes shows up as expectations, and frequently gives us information about what might be going on biologically. Poisson, we talked about, and then of course, well, actually, I'll get there in a second. Facets of distribution, skew. And we talked a little bit about this before, but whether you have less skew, and I don't like the words positive or negative skew, because I don't have a reference point by which to compare it to. And if I'm assuming 0, which is the assumption of normality, then sure, that makes sense. But I don't know why I would want to assume that, because I'm not a statistician, I'm a biologist. And the times that I'm actually studying something that has a mean of 0, in fact, right now I'm having a difficult time thinking of biologically something that would have a mean of 0. And I don't know the answer. So if you can come up with an answer, that's cool, because I love being proven wrong, but it seems like you wouldn't have that. But I do like left skew and right skew. Left skew just means that you have a few extreme small samples. That's cool. Right skew means that you have a few extreme large samples. When we talked at the beginning of the semester, and we talked about sort of annual income, and we talked about this area being one of the wealthiest areas around in terms of average annual salary, what type of skew is being represented in the distribution of annual salary? Is it left skew, where there's just very few individuals that have very, very small salaries? Or is it right skew, where there are very few individuals that have incredibly large salaries? And in terms of salaries, it's right skew. It's absolutely right skew. We talked a little bit about kurtosis. For one, say the word. Say it. Doesn't it feel good? I mean, skew is kind of fun because you can't just say skew. You have to kind of let the you roll out a little bit. Skew, and that is fun. But kurtosis, that's awesome. I mean, that is just a pleasurable word to say, which you never have an excuse to say, except when you're in stats. Kurtosis is lovely. Now, what's that? It sounds like a disease of the spine. Cool. When might we expect to see this type of distribution in terms of evolutionary biology? I'll go to the question in 1 second. When might we expect to see high kurtosis, positive kurtosis, when we're looking at evolutionary biology? Does anyone have a good example? Artificial, well, we could. Artificial selection, we tend to go with directional because we like to make things bigger. We like them bigger. We don't like little tomatoes, we like big tomatoes. Not because they taste any good, they actually suck, but we love big tomatoes. And did you all see the big pumpkin that just won the largest pumpkin ever? Over 2 tons. You saw the big pumpkin? It was pretty cool. It was, yeah. Take a look for the big pumpkin. First, Madison, I'll come over to you, Julie. Bingo. Stabilizing selection, where extremes are selected against, this is what you tend to see. Human baby size is something that has stabilizing selection. If the baby is too small, there's selection against. If the baby is too large, there's selection against. You don't want a 12-pound baby. No, it's just all bad. And I'm not even gonna have it, and I know that. Julie? And I have to ask the simple question, why is it always Florida man that takes the shtick? Yeah. Thank you, Nebraska, for at least sharing some of the honor. Yeah, kurtosis. These will influence what type of test you should do, but more often than not, if you're dealing with some type of skew and you really want to do normality, and you want to do a traditional test, you could do a transformation. I would advise against it, and I'll explain why later. And if you're dealing with skew, either positive or negative, generally it doesn't have that big of a bearing in terms of the statistical approach, but it is, excuse me, important to know what your data are before you go through procedures. The big lovely, Ashley's first choice, normality. One, for some reason, even though I don't know how many of us really want to be normal, that ends up being the cool guy. Two, it is cool because it does look like a bell, and I'll give you that. I like bells, and it's not very often you get to hear bells, so that's cool. But it does have a huge number of clear, clean absolutes. And in addition, it is associated with many of our statistical procedures. If you were to take stats class 30 years ago, you'd be taking calculus, because all the stats is based on the calculus of curves, in particular, normal curves. And it's cool, it's great. It gives us that assumption of the mean, median, and mode, all three central tendencies, they're the same thing. It gives us exact descriptions of population size that fit within the first standard deviation, the second standard deviation, the third standard deviation. That is all good things. That recognition of the second standard deviation provided a strong logic by which we developed that p-value of 0.05. It's still arbitrary, but it is logical. And at least that's somewhat valuable. And really, most of the things that we think about when we talk about normal statistical procedures, we're looking for normality. It's important. So we need to test it. And I'm going to teach you to test it. And for a few weeks, we're always going to test for normality. And then after that, it will become your choice. For a few weeks, we're going to test for normality. And we're going to be testing what is called Shapiro-Wilk test. One of the fun things about most statistical tests is they name it after the researcher who came up with the test. And that's cool. And in this case, it's two individuals, Shapiro and Wilk, that came up with it. And it's a test to examine normality. Now, one of the things you should see in that note is what hypothesis are we testing? What is the null hypothesis in a Shapiro-Wilk test? What symbol represents the null hypothesis? HO. So the Shapiro-Wilkes test evaluates normality where normality is the null hypothesis, which is kind of the opposite we normally think about it. And it's one of the things to recognize about the null. The null means random. It doesn't mean unimportant. The null means random. It doesn't necessarily mean unexpected. Those are different things. And that's one of the places we really confuse ourselves in stats. When you use a Shapiro-Wilk test, you are testing against the null of a normal distribution, which means if you get a large p-value, you fail to reject the null, which means that you describe the random distribution, and that is normal. If you get a large p-value, the data look normal. Opposite with the way we normally think about it. And the reason it's opposite the way we normally think about it is we normally think about the null hypothesis incorrectly. Null hypothesis doesn't mean bad. It doesn't mean unwanted. It doesn't mean avoid it. There are a lot of reasons why the null is good and interesting. In this case, the null is random. And in this case, random is a normal distribution. So when we get a large p-value, we describe the null, which means the data are normal. When we get a small p-value, we reject the null, which means that the data are not normal. Make sense? Okay. I want you to grab the pets data. You already have it. You have it from a previous assignment. If you want to download it again from Canvas, you can. And what I want you to do is I want you to test for normality for the two variables that are appropriate. I want you to open up a new project. I want you to have a code, data, an output folder. I want you to take the data of pets, wherever you have it, I want to copy in that new folder that's associated with this project. I want you to set up the code as you would with that beginning part and with the closing. And then what I want you to do is I want you to test, and there's only two variables that are appropriate to test. I want you to test those variables for whether they're normal or not. That makes sense? All right, so I'm here. Open up a project. Victoria, you see everything that I set up before I start. What do I need to do? What should I first do? Cool. Okay. Do I want to just, where do I get them? Should I just memorize them? Which one in particular do I want to go to here? Yeah, so let's go find that pet script. So I go up to file. I go down to recent. Let me see if I can find it there. No, it's because of all you guys and your homeworks. I'm gonna go into file, go back. Do you remember, I think it's descriptive stats? Okay. And then I find code, I got pets, that's good. So I open up that. Let's copy all of it. Go back into my script. Dang, it's a lot. I don't know what I copied. So let's try that again. Copy. Yeah, that worked. And then let's get the stuff out of the middle. How much of this should I delete? So I'm here. Am I going to keep this stuff 30, line 30 and below? Keep it, but keep it. Always start by putting the beginning and the end. Just get in that habit of the beginning and the end. All right, should I keep this stuff at the top? Yep, okay. How about this? Should I keep this? All right. How about this? Should I keep this? Probably, because it's still probably going to be a factor. So I might as well just keep it to sort of make it good. How about this stuff right here? Do I need this? Nah, I'm gonna get rid of it. Now you could just put hashtags in front of it and therefore keep it in your there, but it won't be red. But I want it just to be clean.
I want it to be clean. So, Haley, am I ready to go? Okay, let's try. All right, so I'm up here. I'm on line 2. I run. Yeah, that worked. That was good. Should I run again? You feeling it? Ooh. Oh no. Oh no. Error. Data pets.csv does not exist in the current working directory. A lot of people send me the working directory. It's not a lot, but like 3 or 4 people send me the working directory. What are you all working directories? Unless you're giving me your computer. Now, if you're going to give me your computer, then you can send me your working directory. But if you use your working directory, work for me. So my working directory right now is user Charles Gunnels. You might know him. Dropbox teaching biological stats in R. ESR fall 2022 for our projects 5_3 evils. Didn't work. What was that? And when we reach a bug, what do? Chandler, what should we do? I love that answer. In my folders. If you look right here, and there were a few people that just sent me the project or just sent me the script. The whole point of sending the project with the folder and the data is so that when you send it to me, it's all there, exactly the way you saw it, so I can run it exactly how you found it. And that's what you want, not only for the class, but just in general. So we're missing our 3 folders. Chandler, give me the 3 folders. Not FATA data. Output. Code. All right. So let's go back. So we already ran the packages, so we're good there. So now we can run df and didn't work. You failed. Oh no, you're good. You're perfect. You're perfect. Jamie? No, so let's actually go down. We'll take a look at data. No, we don't got anything in there. All right, I like that. I like that. So I don't know if you could do this in R, I'll be honest, but I know how to do it here. So I'm going into my finders. I'm going in my CSV. I'm in the wrong one. I'm in a homework assignment. I'm actually in your all's homework assignment. So let's go to my teaching. Biostats. Let's go here, projects. Let's go here. Data. And I'm just going to copy it, just like you said. Then I go back up. I go to 5. I go inside data. And then I paste it. How do we check? What do I do to check, Jimmy? Oh, we can do it that way. Sure. Didn't work. I actually don't have a good answer for that. It just may not save yet. Because I don't know if you guys know this, but we have very fast internet on this campus. All right, so now. Idiot. And that's because I made this 5_3 evils too, which is also dumb. So now we saved it. Well done. Good catch. Let's go back here. Let's see if we can rename this. Can we rename it? I'll do the old school renaming. All right. Oh, I screwed up everything. Yep. So let's say click that, copy, close, don't save, open project. Don't save. Okay, now we have our data in the right place. Now I got to rerun the line because I deleted it. Now we're working. Right. So that was obviously more bothering than needs to be, but you could use your previous codes. We're still running the summaries, and we might as well do the mutates. Someone tell me the value of line 15. Yep, please. Yep. Attaches the name of the variables to the data into R, so that you can actually just use it. Otherwise, you have to put the data frame, $, then the variable name. It's fine to do it either way. This just makes it a little bit easier. And then we do this. Great. So we have a project. Our project has all the pieces. Should I be comfortable at this point? Should I be happy, Jordan? Or should I be concerned? I would say, especially since I decided not to previously. Go in here and let's call this malady test. Cool. All right, like that. So, Gabrielle. Okay, so let's take a quick look at our variables. Which of our variables can we test for normality? Perfect. So either one of these two, we could test when the routing. You could test ratio data, you could test interval data. You test normality of continuous data. You do not test normality of count data, like pet ownership and education. One being nominal, the other one being ordinal. There is no normality of count data. And you don't test normality of identifying data, where subject just identifies the actual person who participated in the study. There's no test for normality there. That's just a code for that individual. So we test percent vegetarian diet, or we could test animal view. Love it. So tell me what to do. All right, I can do that. No, let's see what happens. This is part of the fun of R. You do things, you see what happens, and then we sort of figure out what. So we see what happens, and what happened. It's not continuous data, so it didn't like that. Okay, so what do I do? It suggests to me that I did not do attach yet. Okay, now we can do. And what's the other one I should set up? Julie, what do I have these weird forward quotes? Yeah, because on spaces, you have to tell R that this is actually a object to work with, not two separate things. So you did a little forward quotes. What is an alternative way of fixing that, Julie? Get rid of spaces, and where would you get rid of the spaces? You get rid of spaces in the Excel. You can also mutate it, where you can just make it animal view as one word equals the forward quote animal space view. So should we try this? All right. And let's try animal view. All right. Dominique. What did we learn? Sun vegetarian diet has a p-value of 2.2 times 10 to the negative 16. Can you please tell me what number that is? Basically. 0. So, is that a small p-value or a large p-value? Small p-value. This is what we do with p-values. Since it is a small p-value, do we describe the null or do we reject the null? We reject the null. If we reject the null, what hypothesis do we describe? The null or the alternative? Alternative. All right, so this is a small p-value. So we're going to reject the null. We're rejecting the null. In this case, what does that mean that we are rejecting? This is normal. The null hypothesis is a normal distribution. We are rejecting the null. That is telling us the data are not normal. Cool? Make sense? Okay. So, Lucy, what about with animal view? Animal view. P-value, large or small? Very small. What number is that basically? 0. What is the chance you will make a mistake by rejecting the null? A chance you'll make a mistake by rejecting the null. 0. Can you reject the null? Absolutely. What's the null in this case? No, what is the null hypothesis in this case? It's a normal distribution. So are these data normally distributed? Oh, heck no. Heck no. Okay, so if you remember, we started with this assumption. Many statistical tests require normality. We've just looked at a study based on 3,000 people in the United States, and in both of our continuous variables, we have just rejected the null. These data are not normal. Can we use traditional statistical approaches to evaluate these data? No. So what do? We panic. That is exactly right. Yeah. You really do want to always look at your data before you do test. And you maybe eventually just look at like a histogram. And in fact, I would more often not encourage just look at a histogram over a Shapiro test. You will do Shapiro tests because we are taking a class together. You should know that operation. If other people ask you about it, you should be able to do it. But you should look at the data, look at the distribution, create a histogram of the data. Anyone create a histogram of the data? Can someone coach me through that? Because I'd love to see a histogram. Anyone? Yeah, Gabrielle. Try colors. And did anyone try any fun colors? Like, did anyone get a rainbow or terrain yet? Let's say it's terrain colors. That could be good. Let's see what we get there. Is that pretty good? I don't know. Oh, that is not good. Let's try 25. Oh, let's try this. Well, n equals 25. I don't think that's going to be good enough. Run that. Oh, yeah, it's pretty good. Pretty good. Is that pretty good? Yeah, it looks pretty good. You want to do more? 50. 25. Oh, that's not good. I don't like that. I will be happy to. Bin is how many bars go into your histogram. So we said create a histogram for percent vegetarian diet. use this function called terrain colors, and let's use up to 25 colors along a gradient. That gradient, as you can see, is from green to orange, and then bin up to 50 times. Now, what the program will do is it will bin up to 50 times, but if there's a better binning that shows the data more clearly, it will use that. So that's what we get out of here. And remember how to fit a curve on top of that? A normally distributed curve on top of that? Anything like curve? D norm? X? Mean? Set vegetarian diet? SD? Mean? Set vegetarian diet? Add? Equals true? Color? Maybe 2? Line weight? 3? Line type? Maybe 2? Want to do it? I don't know if this is going to work because I'm just trying to memorize, but we'll see. Oh, something happened wrong. Expression did not evaluate the option. Someone, I think I hear some. No, we don't have to do that. We'll just let that go for the time being. Let's do our other one. Let's do another histogram. And this time, let's do view. Let's do rainbow. I think it's rainbow color, but it might be rainbow. Oh no, there it is. All right. Okay, I simplified the code a little bit for the histograms. Our p-value for Shapiro test of animal view is basically 0. The shape of our histogram. Does that look normal? Normal. I know. The p-value is basically saying 0.
Would that be like skewed to the left?
A little bit. Very normal. A little bit. Very normal. A little bit. What about this one? Percent vegetarian diet. That p-value is basically what? It's 0. I'm just going to scroll up there. Show you that again. 0. Does that look normal? A little bit. A little bit. I'm going to save this as you guys are typing up a little bit of the code. I'm gonna remind you that I have in the code folder, the script. And in the data folder, the pet. And I'm gonna do a little trick. It's kind of a fun little trick. I'm gonna save this image. I'm gonna save it in my output. I'm gonna call it this % veg. And I get this cute little picture now that is saved for me for later. And it's my output folder. You know what time it is? I'm very sad to say. Class is over. I will leave you on this one very important note. You're going to have to test for normality until we get to a point where you don't have to test for normality. Right now, you got to test for normality. Normality is not always what you think it's supposed to be. And actually, I think those data show that very nicely, especially for vegetarian diet. When we test for normality, we get a p-value that is shockingly small. We'll talk about it in detail, I should say. But the larger your sample size, the less likely you are going to get to determine over the future. Well, you're not going to get a small p-value. Small sample sizes, you will generally not be able to detect normality. You'll get a larger p-value. It's because it's small sample size. When you look at the curves, they kind of look a little normal, but then again, you're also right, a little skewed and get that little weird bumpy thing that was going on in some vegetarian diet by the vegetarian sort of section of people. Maybe that difference between vegan and vegetarian, where the vegans were identifying some dairy. But kind of normalish. Big take home ultimately. There are ways to work with the data very easily, very closely, and really flexibly. Okay, you test and then you decide. Have a good weekend, enjoy the test. I'm going to ask for a requirement that you guys take the CodeBook test first, then the open book. Just because. I'm going to say it again, issues locked on browser. If it is buggy for you, do not panic. Do not freak out. Remember Hitchhiker's Guide to the Galaxy. If you are concerned, just reach out to me. No big deal. If you tell me honestly that there was no issue, we're done. I don't need to see any evidence beyond you just telling me there's no issue. Okay? Have fun. You're in virtual land. Have a great day.